on to chapter 9, regression analysis. At the end of the class, I'll give you back your tests and quizzes. I just want to make sure we get through this first. But yeah, pretty much everyone did better on the second test than on the first test. Probably a little too easy. Now I'm going to have to make the third test like super hard. I have to make it look realistic. I can't like have everyone pass in the class. That's just crazy.
That's great. That's a good record. Like, my kids learn.
You have to like make the third test like super hard.
We study more.
Yeah, so yeah, pretty much everyone had their first test grade dropped because everyone did better, you know, except for a couple overachievers who got like hundreds in both. Yeah, so that's good. I'll return those to you at, towards the end of class. I forgot to arrange them by name, so now I'm gonna like call your name like 4 times and give you back everything. But yeah, we'll take care of that at the end of class. For now, we're going to move on to chapter 9, where we're going to sort of apply things that we learned in chapter 8, make it more concrete. We're going to end up with, we spoke about, you know, trends and sort of fitting a line to it, but what is that line? Now we're going to find out how to find the equation of the line that best fits this point and what that line can tell us. It's going to help us to predict a lot of things, so that's what we're going to do. So basically in this chapter we're going to cover so-called regression lines, which are the lines of best fit. To scatter plot. Right. We are also going to use regression lines to make predictions. And we'll see how that works in a bit. It's just going to be a matter of evaluating the equation of the line at a certain point. And we can sort of predict what's going to happen in the future based on what's happening in the past. Not always 100% accurate, but usually it's accurate enough. The typical approach to this problem, being able to find the equation of the regression line, is called the least squares method, or method of least squares. So the idea is the following. So, picture here, let's say we have a line of a bunch of points. So we're going to take a vertical line. We're going to call that distance D1. Vertical lines that hit this, that distance is D2, D3, D4, and so on, right? So the magnitude of this sort of represents the distance of each point from the line. Now we want it to fit all points pretty closely at the same time. So what we want to do is make the sum of all these distances as small as possible, right? And using the distance form, we have square roots all over the place. So that's why we take the squares of the distances to just make the computation easier. If we minimize the square of the distance, it's the same as minimizing the distance itself. And so that's basically what we're going to be doing, right? So we're going to sort of come up with a formula that will give us this sum. Okay, so let's come up with the formula. Are one of the lights off?
Yeah, let's do it.
It's really dark. Yes, to both. Okay. Here's the line. Let's look at D1. Let's call this point x1, y1, and this point here is the equation of this line, and we're going to call it y equals ax plus b. Sorry, they use a plus bx. That's their general form. So here, this would be x1 comma a1 plus x1. So that's all the points on this line look like this. A random point would just be that coordinate. And so the distance here is just going to be the absolute value. We're talking about the vertical distance, right? So absolute value of the change in y. So basically we're going to say this is a plus bx1 minus y1. So this is the y value for the line minus the y value for the point. Take that in absolute values, we get the distance. That's just going to be the vertical distance. This means the sum of the distances is, we call it f of a, b. And it's going to be just adding all these guys. Sum of the square distances. So a plus bx1 minus y1 squared plus a plus bx2 minus y2 squared plus dot dot dot.
So what does that say? Some of the what?
The square distances. Right? That way we don't have to worry about signs or anything. It just gives us a nice number to work with. And so this is called, by the way, they call this the fitness line. Let me just write down the definition, then I'll talk about it a little bit. Finding what's called the least squares regression line for the points x1, y1, all the way to xn, yn is the line. So basically the idea is we have a bunch of scatter plots. We want to be able to figure out the line that fits them the best, right? So what we did was we measured all the distances between all the points. And we're just going to measure the distance as a whole as the sum of these distances. And basically what we want to do is minimize that. So figure out a formula that gets us the distance. This ultimately gives us this formula when we square them, and that gives us the nice numbers and all that. We don't have to worry about radicals or distance formula or anything like that. And so we call this the fitness. Now, the best fit line is the line for which the sum of these distances is as small as possible, which means we just want the fitness to be as small as possible. So basically, if I can figure out what values of a and b I can choose so that that function is as small as possible, that will give me the best fit line. Okay? So the idea now becomes we need to figure out what a's and b's will fit this the best. So when I say, okay, the line that we need to find is this line for which this is as small as possible, sort of vague. Give me a formula for it, basically. Right? So let's do it. We can actually find a formula for this. The problem is, you sort of need Calc 3 to do it. We're not going to deal with the derivation. You actually need multivariable calculus because both your x and y's are variables, so you have two variables at the same time. It's sort of weird. You have to do what's called partial differential equation. But take it on faith that we can use multivariable calculus and we can solve this. And we can pretty much give you a formula for this. Put this in a theorem called Theorem 1. Suppose the regression is y equals a plus bx, then 1, b is going to be r plus y plus x, 2, that. Right, so remember back in Calc 1 when you had a function you wanted to find the minimum value, you find the derivative set equal to 0, do all that stuff. If you do the equivalent thing in Calculus 3, which you've never taken Calculus 3 so you won't know, you can pretty much find the minimize this function that I mentioned, and you will come up with these 2 points. You can actually figure out the point that the line will pass through will actually be the coordinates for the averages, the mean averages. And the slope will be given by this formula. So that actually can tell us exactly which line will be the best fit. We minimize it, these are what we get by going through the calculus. You can read the appendix if you want. They proved it in the appendix, but you don't really have to know the derivation because, like I said, it's Calculus 3. We're going to use these formulas soon. Get some notation. Because you might see this notation used in your textbook, so I want you to know the value r sy over sx is denoted. It's called b hat. Right? Just be a little carried over it. Right? And plus. So finally I can give you the formula for the equation of the line. And then we shall use it. So this gives us theorem 2. Y minus y1 over x minus x1 is equal to b hat. Right, these are just using the equation of a line because we have a slope and a point, so we can use the equation of a line. That's y minus y1 equals mx minus x1. Or y is equal to y bar b hat x bar plus b hat x. So yeah, we did a lot of hand waving here because really you need multivariable calculus to derive all these formulas, but they can be derived. You can see them in the appendix of the textbook if you're interested. So the idea is we have a line, we want to figure out the best one. So you measure all the distances, you add all the distances together. You use calculus to minimize the function, and you end up with these two properties here, right? So it turns out that with these values, your function will actually be minimized, and all we do is plug that into the point slope form for the equation of a line. And we can write the equation of the line in any of these. Of course, you plug in x equals 0 and solve for y. You get the y-intercept would be, it's called a hat. So the regression line can also be expressed as y equals a hat plus b x, if you want. But I'd rather memorize one of these.
For 3, why isn't it just the second equation plus the mean of y?
The second
Why is
equation-
it like, why is like the y bar minus b hat times x bar, like why is that segmented?
Oh, I expanded the brackets. Yeah. And I grouped, these guys are constants, so I just grouped the constants here. And then the guy that's attached to the x I did it separate. I just wrote in y equals mx plus b form.
Okay.
So, yeah, so it's just a nice way to write the form. But yeah, at the end of the day, these are the important things to know. Boom. And you need to remember how to find the b hat, right? Which is just r times this s. Remember, s sub y is the standard deviation for y. S sub x is the standard deviation for x. And your b is actually r times sy over sx. Once you can find that value and the values of the means, this will actually give you the equation of the line that fits it the best. It's a lot of writing, might look complicated, but actually in practice it's not that bad once you know how to compute all these values. So let's actually do an example. So we're going back to that example I gave you in chapter 8. Before spring break, seems like forever ago, but I can just remind you of the particulars. We computed these. We had that x bar was 73.5, y bar was 73.6. We also computed the standard deviation, which is 15.12. We also computed standard deviation for y, which was 14.08. And we also computed the R value, which is 0.766. Okay. So the important thing here is you might be given these, but you might not be given them. So you need to know how to compute each of these values, right, from the formulas. So this is just the standard deviation for x. You know, you take that square root of the average distance. Same thing for the y. This is the R value, which is the covariance divided by the standard deviation. Right, so make sure you remember all the formulas for this, because we're not going to tell you the formula, they expect you to remember them. Right? So if you're not given these values, you should know how to compute them. It's possible for them to not tell you outright. Right? But once you have all that information, then finding the best fit line is just a matter of plugging them into that formula. Right? So let's actually do this. What do we want to find first? Let's find the b hat. Now b hat is r times sy over sx. Huh? It's very dramatic. Okay, so r is what? 0.766, right? You're at the computer, it's given, you just plug it in here. Your standard deviation for y is 14.08. Then you divide that by the standard deviation for x, which is 15.12. And I computed that, and you would actually have 0.713. So now to compute the regression line, we use y minus y1 equals m x minus x1. Right, those are the points that we're using. So it's y minus 73.6 equals b hat, which is 0.713 times x minus the average x value. And this simplifies to y is equal to 21.19 plus 0.713x. Yes. It was getting too cheerful.
Can I take that class?
Yeah.
I feel like I should be skipping while I'm writing with my little flute or something. Okay. All right, so that's basically the answer. You have these values, you just plug them into the formula. Right? So yeah, once you see the derivation, you're not going to be asked to derive any of this, but you should know the formulas, and then you're just applying them. Right? So once you find the b, you just plug it into the point slope form, and it gives you the equation right away. It's just arithmetic from here on. Now, one reason why this is important is because it helps us to predict things. So that's the next thing we want to look at. Of course, you can never be super sure because you can't really predict the future based on the past, but for some things that seem to always behave a certain way, we sort of do it. And a lot of the times it's good enough. So basically what this means is if your x and y represent something in particular, then you can sort of predict what's going to happen with these things. So the idea. So if this is like your scatter plot, x versus y, and these are all your points. You see like there's this general trend happening, and someone asks you about, what do you expect to happen some here? T is sometime in the future. Or T sometime in the future. Someone can sort of say, what do you expect to happen? Well, if I take this best fit line as a predictive measure, I would expect the point to be on this line. So basically we're going to use the point on this line, predicted. So this is a point that might not yet exist, but I'm saying if in the future I make my measurements, I sort of expect things to fit this line because they've sort of been doing that in the past, right? You sort of expect it, Every time you drop a rock, it falls to the floor. You sort of expect the next time you drop a rock, it's going to fall to the floor. This has always been happening. And you sort of make this projection. So basically this line is going to, any future points you'd assume would fall on this line. So that's sort of how we do the predictions. So y value predicts the average, the regression line predicts the average y value. Because we use the mean to figure it out. And the best fit regression line will actually always pass through the coordinates for the mean, it turns out, coincidentally, if I do in the calculus. So we did the first example where we looked at the 10 grades and we found that this was the best fit regression line for this set of 10 grades. Now a follow-up question could be something like this. if you recall the question from chapter 8, I had a list of 10 grades, but for each student there were 2 grades, right? There was the grades from exam 1, and there was the grades that they got from exam 2, right? So now let's say I have this new student. I know he scored a 78 on the first exam. I want to predict how he will do on the second exam. So, you know, final grades are due. I lost the second exam, so I don't know what the student got. Like, holy crap, I gotta make something up to give the student a grade. So I'm like, well, on average the class did this well, so let's sort of predict on average how well I think this student would do, so I can make up a grade.
Is this what you actually did?
No, I've never done this actually.
Yeah.
Look away.
I'm totally kidding right now.
I've never done this.
Thankfully, I've never been in the position where I've lost grades. So.
I had a professor who lose every single exam, for like all 3 exams, and then he gave everybody an average grade based off what he thought you deserved, but he never had, it was like a 300-person lecture class, and then the school offered the chance to take it on the 4-week summer session for a 300-level microbiology class, and you could only take it that session, which started in 2 days for a retake. This was not here, but
Okay.
this was in Monty Hall.
Because he probably wouldn't still be around unless he had tenure or
No, he
something.
was asked to retire for this semester. He had like a lot of like credit,
Okay.
so.
Yeah. Well, this is sort of a joke. I was saying that Dex can't really do that anyway. But yeah, let's pretend, I was trying to be sneaky. I know what he got in the first exam. Let's try to guess what he should get on the second exam so I can make his average and give him a grade. Okay? So I know they got a 78 on exam 1. How do we do it? Well, given that we know y is equal to, what did I say equal to? 21.19 plus 0.13x. So y, remember this was the exam 2 grade. Right? In the example that I had from chapter 8, the y-axis was the exam 2, the x-axis was exam 1, and this is the exam 1 grade. Based on our setup from the last lesson. Right? So the idea is, if I sort of know the exam 1 grade, I can figure out what the exam 2 grade should be, assuming that the grade will fall right on the line, right? The student will perform on average as good as everyone else. Right? So this means if the student scored 78 on exam 1, the expected exam 2 grade would be y is equal to 21.19 plus 0.713. Just plug in the exam 1 grade here, 78. And so I worked that out, 76.8. So yeah, if I had to make up a grade for the student, that's the grade I would have made up. Like if that were to happen, I'm not saying that would
They're
happen.
wrong, like they didn't even fill out the exam.
Well, the means would go up higher, so this should have gone up higher.
So yeah, a student who scores a 78 on the exam 1, this is how much you'll expect him to score on exam 2. If you didn't have knowledge otherwise. Another way you can do this is a professor could just tell you, in the past, this is how my class performed. So you can sort of judge, you're worried about whether you should drop the class or not. You say, well, I got a 70 on exam 1. What do I have to get exam 2 to pass? So the professor could say, oh, well, you got a 78 on exam 1. You should expect to get this on exam 2. Because I've taught hundreds of students in the past, and this is the line that describes their grades on average. So you should expect to get this, and then you can make a decision based on that. So that's when people are wondering, well, I don't know. You know, sometimes students have these unrealistic expectations. You know, yeah, I could get an A. Well, that's what you should expect. Plan based on that, right? So one of the things with statistics, why it's useful, it turns out that everyone is different, but everyone isn't that different. Turns out how most people perform, odds are, if you had to bet on it, that's how you would perform. That's why this statistics is even useful in the first place, because you can make predictions based on how a lot of things have happened. You can predict it, and it's pretty accurate, usually. Yeah, so that's basically it. That's basically all we need for chapter 9. It's just those formulas to be able to get to this regression line. And once you have this regression line, you should be able to make predictions based on some input. So it'll usually be given in that way. They'll give you all this data. They may or may not give you all the mean, the standard deviation, the R values. You'd have to compute those if you're not given them. And then you use these formulas to get this line, and with that line you can make predictions. So in part A, they might say, oh, find the regression line. And then part B, they say, oh, suppose this happened. You know, what do you predict will happen in the future? Right? That's what this sort of question would look like. So Lily was asking the difference between S and
Theta.
it's
No,
sigma,
Sigma.
right? So it's like that. Well,
It's like small sigma.
like if you're writing by hand, that's how you use it. All right. There's another thing that you might see. There is something called there's X bar and then there's mu. Those will typically mean the same thing. So S is usually referring to the sample standard deviation. And sigma would be the population standard deviation.
So if it's
Right, so in this formula, you do that radical, the top would look the same, but you have divide by n here instead of n minus 1. Remember, this formula had blah, 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 divide by n minus 1, because it actually takes out bias by doing that. The idea behind these two are the following. If in theory you could find the standard deviation of everyone in your population, this is the value you'd use. But often this is not the case, right? So if you're doing a study on all Americans, you know, are all Americans obese, right? There are 300 million Americans, right? You're not going to go measure everyone's weight, right? So what you do is you take a sample, right? You only study 10,000 of these Americans, right? So when you take the standard deviation for that sample, this is the standard deviation you use. It's really just an approximation of this one. So the idea is sometimes you can't collect your data from the entire population you're studying, so you take out a sample, and then the standard deviation would actually slightly be different, right? So you'd use this one in your predictions as opposed to that one. And there are formulas that can take you from one to the other, and we'll probably talk about that later. Similarly, this would be the sample mean, and this will be the population mean. And in general, they're assumed to be the same. So in general, you'd assume that the average is a well-behaved thing, right? And there are things like the central limit theorem that sort of tell us this, that the average is sort of predictable in a certain way. Right, so whether you're measuring the average of a population or the sample, if your sample is large enough, representative enough, you'll expect it to be the same thing. So if you see these two notations, they're really the same thing. The difference is one is for a sample, for a small segment of the population that you're doing your study with, while the other one is in theory, if you could do it with the entire population. Right, so that's sort of the difference. Now, with that said, we are going to completely switch gears now. So we've gone through the calculus part of the course, we've gone through, this is everything we need to know from the statistics part of the course. Now we're going to do the probability part of the course, starting with chapter 10. Theory. Probability and statistics go hand in hand. A lot of the times you need probability to help you out with statistics, so it's worth studying in its own right because statistics is useful and probability helps you do it. So, let's see. Probability is also affectionately known as mathematics of gamblers, right? Turns out, it's strange, but a lot of math had really strange origins. It turns out probability theory was entirely developed to be able to gamble, believe it or not, right? So, obviously there are these games where, for example, someone can, try to bet you money, say, okay, we're gonna roll 2 dice, right? You roll 2 dice. If the sum of the dice added to a 7, I pay you $2. If it adds up to anything else, you have to give me $1, right? So there's this idea of a game. You want to gamble, right? Make some money. You're hustling with the street vendors and stuff like that, right? So you're like, is that something you should take, right? Is that a deal you should try to make? Well, maybe I should roll the dice, right? You're not sure. So eventually these games are going on. After a while, people were like, am I being hustled? Like, am I just being stupid playing this game, right? So how do I know if I have a good chance to win? Well, then they went to the mathematicians. Like, yeah, there's this game, right? The guy told me if I roll 2 dice and I get a 7, he pays me this. But if I get anything else, I lose money. And then the mathematician starts to think about it and then come with an equation. Is like, you'd say, yeah, you should play that game. You actually have a good chance of winning. Or, no, hell no, he's scamming you, right? So probability was sort of the math that developed into figuring these things out. It's the mathematics of chance. What is the likelihood of something happening? How likely are you to actually get the 7, right? How likely are you to not get the 7, right? Or if you're playing 21 or poker, how likely are you to get a full house and actually win the game, right? How likely is it for something to happen? Whenever you ask questions like these, what are the chances of something happening? Well, then you're in the realm of probability. And it started out by people wanting to gamble, but eventually you realize that, it's actually a lot wider than this. And it actually goes with statistics. So sometimes if you did statistics, this is where people can say, if you smoke a lot, you have like 2/3 chance of getting lung cancer or something like that. Basically what happened is people did a bunch of statistics, did a bunch of studies, and they're like, okay, of all these people that we know smoking, right? We collected a sample, we did the standard deviation, the average, all that, and we figured out, 66% of these people who smoke over 10 years' time, they get lung cancer, right? So then they make a prediction, you're 2/3 likely, 2 out of 3 people who smoke will get lung cancer, right? So they can say that. And basically what you want to do, if you want to capture that information, you would actually say it as a probability. You'll say, you know what? You have a 66% chance to get lung cancer if you smoke, right? And that idea, 66% chance, is called a probability. And, so let's just talk about, loosely speaking, the probability of an event is the chance or likelihood of the event occurring. What are the chances that you'll get lung cancer if you smoke? What are the chances if you actually roll 2 dice, you get a sum of 7? Right? Answers to these questions are answered by probability. Right? So what else I want to do? It is always a number between 0 and 1 inclusive. Right? So 0 represents 0% chance, and 1 represents 100% chance, right? Certainty. Right? Of course, figuring out 100% certainty is very difficult in actually real life. You'll never actually get it, but in theory, you can get 100%. But it's always going to be between 0 and 1. There's either no chance, or if something is certain, it's 1, right? It's always a number between 0 and 1. Always, right? You can never have a probability outside of this range. So, and they even put it in the syllabus. If I ask you for a probability and you give me a number outside of this range, 0. I'm just not going to listen to anything else you say. Well, the probability is 5. Nope, you have no idea what you're talking about. Okay? It will always be between 0 and 1. If you don't get a number between 0 and 1 when you're computing a probability, you made a mistake. Right? You have to do something else. So, here's a fuzzy but more workable definition. Let A be an event the probability of A, or in other words, the chance of A occurring, is denoted P and in brackets A, right? This means the probability of A, right? And is given by So if you have some way to get your hands on these 2 pieces of information, you can actually compute the probability of A. So for example, going back to that definition I mentioned before, going back to the example I mentioned before, you roll a dice, you want to figure out the sum of 7. What you have to do is figure out what is the total possible number of scenarios that could happen, right? You can have a sum of 2 or 3 or 4 going right up to 12, right? Because the die has 6 parts, right? And you count all those possibilities. Count the number of ways you can actually get a sum of 7 out of those possibilities, and when you divide them, you actually get the chances of doing that, assuming everything is equally likely, which I'm going to mention soon. We're still in the fuzzy stage. We're going to be making this more precise in general. I just want to, this is probably theory 1, chapter 11. We're going to probably theory 2, and we'll make everything a lot more precise. But right now, I just want you to get the idea of how we're going to measure these things, right? Figure out the number of ways what you want can happen. Out of the total number of possibilities, you say, that's the probability. So when I say, you're 66%, there's a 66% chance for you to get lung cancer if you smoke, that means 2 out of every 3 people, right, will get lung cancer, right? So we're going to be making that more precise. I don't know if those are the actual stats, I'm just making them up. They say 88% of statistics are just made up, which I just made up that 88% as well. Okay. All right, so another thing I want to mention is that events are usually denoted by uppercase letters. Let's do a simple example so you can sort of see how it works, and then we will get into some more complicated, fun stuff. Okay, so 35 out of So some probabilities just come from statistics. So what you can do is, in this case, let's say we surveyed all 40 students. Okay. So somehow come by the statistics that 35 out of 40 students love Jhevon. Right? The other 5 thinks he's crazy. You know, if you pick a student at random, right? Random means all students are equally likely to pick, right? You close your eyes and you pick someone, right? So they're all equally likely. What is the probability that the student actually loves Jhevon? Well, you could say let A be the event, right? Events can be used in a very broad term. The student. Then we can say that the probability of A, the likelihood, the chance of someone loving Jhevon is 35 out of 40. Right? Because this is the number of ways what you're looking for can happen, right? There are 35 students who possess the property that you're looking for, and the total possibilities are 40 students, right? Because you're choosing from this class. Within context, only 40 people exist in your universe. 35 of them have a property that you want to look for. And so the probability of that property occurring is just 35 out of 40. Right? That's just. So. Now we begin with the warning, because we're going to be going into probability. And again, we're going to be obtaining sort of formulas and rules for doing things. And it's going to be really important that you follow these formulas and rules. Probabilities can often be counterintuitive. So I know I made it look easy here, but there are a lot of times where your intuition will fail you. So follow rules, formulas carefully. we reason logically, for crying out loud, right? We're going to start to talk about what logical reasoning means as far as probability is concerned. Example, a while back there was a famous probability problem that, I mean, when it just came out, even like a lot of people just like, that's crazy. You know, it's a very famous one. You probably heard of it. The Monty Hall problem. Anyone heard of that? Anyone? Anyone ever see the movie 21?
Yeah.
Jump Street?
No, 21. Huh? Well, the MIT student who gambled to try to make his money to get into Stanford or something.
I remember the previews.
Right, well, Kevin Spacey. Right, this was the question he posed to the students in his class, right? And a lot of people find it confusing. So here's the setup, right? We have a game show. Monty Hall was a famous game show host. It's sort of based on a game show. You have a game show. There are 3 doors. Right? So you have door number 1, and door number 2, and door number 3. You must pick a door, right? So here's the idea. Whatever door you pick, you get the prize that's behind the door. So the trick is, behind one of the doors is a car. Behind the other 2 are goats, right? So behind one door, there's a car. Behind the other 2, goats. So you will get whatever is behind the door you pick, right? So that's the idea. So now here's the question, right? So scenario: you pick a door. Doesn't matter which one. Let's say door number 1. Right? Now, what the game show host does is he doesn't just say, okay, open door number 1 and gives you, right? What he says was, Monty opens another door. To reveal a goat. Then he asked you, do you want to switch? Right? Now the question is, should you? Right? You know that show, Let's Make a Deal? Right, it's also a simple problem. There's like 3 curtains, you know, it's like, you know, behind one of these there's like a living room set, the other 2 have zonks, you know, and you pick a door and it's like, oh, behind this door there's a zonk, and you're like, oh my god, you sure you want to keep that door, right? So you have 3 doors, 1 has a car, the other 2 have goats, you pick one. Okay, door number 1, Monty, I want door number 1. And he's like, okay, you pick door number 1, and he goes, boom, behind door number 2 there's a goat. You sure you want to keep door number 1? I just showed you a goat. What if this is a goat, right? Now the question is, should you actually switch the door?
No, you have the same chance that you did in the beginning.
Yeah. No, because you had a 33% chance initially, but now you know that it's a 50%. So you increase your likelihood of being
I
right.
feel like it's the same though, because it's like, regardless if you switch, you might switch the club. So.
The answer is, drum roll.
No.
Doesn't matter.
Yes, it matters. You have a better chance of winning if you switch your door.
Why?
Which, it's like I said, it's counterintuitive. So you have to be careful when you look at these problems.
Does he always ask you to switch?
Yeah, this is the idea.
Always, every single
He'll
time.
always ask you
Even
to
if you
switch.
pick the car the first time.
Yeah, he'll ask you to switch. So the idea is, so now it turns out, it might not look like this, but this is a probability question. You're really asking, what are the chances that the car is actually behind the other door, right? You have to sort of figure it out. It turns out now the chances of it being in the other door is twice as likely once he shows you one of them.
Then all
And
the
it
doors
doesn't
are
seem to make sense,
Oh,
but
because it was 33 chance then I would say.
right.
I
So
understand the
Because
percentages,
the one
but
door
like,
is 33 and the other one becomes like 66 then, right?
exactly,
Yeah.
right?
Where?
So let's say he has the 3 doors.
There's
Why?
a
Why does this even
30
make
chance
sense?
that it's behind.
So it's not like, oh, well, you know,
Yeah.
he didn't change what's behind the doors.
Right,
Why should it
exactly.
change the chances that you're right? It doesn't make sense, but mathematically, it's actually more beneficial to change, right? And why is that? Well,
Because there's,
let's say you have the 3
Something
doors,
about-
there's a 66 chance getting.
right? Door 1, 2, 3.
Go.
Let's say you pick this,
I feel like you're just switching to the.
right? What are the chances that it's the car?
33%. 33%.
1/3.
Is 1/3,
Yeah.
right? So you have a 1/3 chance of being right. Right? Which means here, there's a 2/3 chance the car is here. Right? So there's a 1/3 chance that the car is here, but there's a 2/3 chance that it's over there. Now, if you pick this, but he opens this door, and you're like, there's a goat here. Nah. Right? There's a goat behind door number 2. So there's still a 1/3 chance
Yeah.
here. That didn't change. But guess what? Now, there's a 0 chance of the car being here, because you can see it. There's a 0 chance of the car.
So that's 2/3.
Which means, if there was 2/3 over here,
Is that?
and this door is not a factor, it means there's actually a 2/3 chance concentrated on this door alone.
What
That
did it?
means there's the 2/3 chance for the car is concentrated here.
Even though.
Why wouldn't it be 1/2 and 1/2? Why wouldn't it change to that?
Because the objects behind the door never changed.
Yeah, but now like it's a different scenario where
It's
you're
not a
choosing
different
between 2 doors. Now he's like, do you want either 1 or 3 as opposed to 1, 2, or 3?
No,
Right?
it's always, you had
He's
to
saying
choose
you
between
could
3.
choose door 2 now still?
Well, no, you just
But
want
it's
to choose
not
the
3
switch.
doors. Now it's 2 doors.
But
Now,
the
and it's-
original
The
chance
chances
of it
all
being still 3.
concentration. Like they all concentrated the chances on the last door.
Yeah,
Because
it
There was
didn't
always
change.
a 0% chance for 2.
No.
Yeah, you never knew that.
know
But you didn't know.
But it's not a 2/3 chance anymore. I don't think.
It's actually fixed.
Crazy.
And it turns out, like, this is the main argument, this is the short argument, but you could actually write down all the possibilities. You can say, suppose I pick door 1, but it's behind door 2. What would happen? And you can list all the possibilities, and you realize 2/3 of the time, it's better to switch doors. You can actually do it, right? This is sort of the short way, but the idea is, when you pick, there's a 1/3 chance the car is here, 2/3 is over there. If you know it's not here, it means the 2/3 has to be concentrated on this door. So you're actually twice as likely to get the car if you switch. I know it doesn't make sense, it doesn't seem intuitive, but if you don't like the math explanation behind it, you can literally write out all possibilities. Right?
That's true.
So you could do something like,
Yeah.
I don't think.
But the chances were so much different that most people watching the game show would realize that people who switch have their comments.
the people
But
who
again,
what?
it depends on how often
On
people
deal
switch
or
or
no
not.
deal though, you gotta, usually when you keep it, you get that in easy. I don't know.
So I'm just going to use C for car, G for goat, right? So
G.
goat, car, goat. We can have goat, goat, car, right? Those are all the possibilities, right? Now, let's say, I just want to make it simple. Just say pick door 1.
say you pick door 1, right? Now what are the options? Let's say in the first case, you pick door 1, right? So these are the cases, case 1, case 2, case 2, right? So in this case, if you pick door 1, in case 1, if you switch, what happens? You lose, right? So that's just one case, right? Let's talk about case 2. You pick door 1, that's a goat. Now he'd have to show you door 3 that there's a goat, right? Which means now if you switch to door 2, you get the car. Let's talk about the third situation. You pick door 1. He shows you door 2, which means if you switch, you get the car. So it turns out switching makes you win 2 times out of 3, right? It's actually it's better for you to switch, right? Now, when I just asked the question, I was like, no, you don't switch, there's no difference. No, it actually makes a difference, right? So that's what I'm talking about. Probability, it can be counterintuitive, and this is where a lot of students fall down, but you have to just think of things really logically here. I mean, when you throw in, not everything is as predictable as this. When you throw in human nature and human beings, and then you start to think, does the host actually know what's behind the door? Is he trying to trick me? You have to think about this emotional game theory edge. It's sort of different, but all things being equal, all things being equally likely, probably says this is the best strategy. If you want to win the car, you should switch the door. Right? It turns out you're twice as likely to win if you do. So, there's another similar one. 3 prisoners, right? 2 will be executed. 1 will be set free. Can't spare the taxpayers' dollars to electrocute 3 people, so I have to set 1 person free. So now, here's the situation. 1 prisoner is freaking out, right? He asks the warden, who will die? So now, the warden says, the warden has 2 conditions. Can't tell you your own fate. And can't tell you who lives, but he'll tell you who dies. I will tell you 1 person who dies. Right, so you have prisoners A, B, C. Let's say A is you. And he can't tell you about you, so A asked the question, right? And let's say warden says B will die. Now the question is, should A relax? Can he actually sleep soundly tonight? Before, he had a 1/3 chance of surviving, but now he knows for a fact that someone else is going to die. So it would appear that it's only 1 out of 2 now. I'm actually in a better position.
The decision's already made.
No, wasn't it 1/3?
The decision's already made.
Yeah, but this is all you know. So
You
it's
can't-
sort of like, it's very similar to the Monty Hall problem, right? Like, what's behind the door was already set before you even did anything, right? But just knowing this new piece of information completely changes your chances, right? So the question is, if A knows that B will die, is his chances of surviving actually increase? Should he relax a little bit?
Because you can't switch, so if he's gonna die, he's gonna die.
Yeah,
So he might as well relax.
Geez, have some hope in your final moments, for crying out loud. Should he get a good night's sleep, or should he, be praying or something?
It wouldn't matter because it's already chosen.
Well, it didn't matter before.
It turns out,
Yeah.
I'm not going to show you the solution. I'm just going to annoy you guys by telling you the answer, and then you try to have you figure it out. Turns out, A has the same chance of dying.
Yeah, because he can't switch like the doors.
That's not the crazy part. Here's the crazy part. C is now twice as likely to live.
That makes sense.
So yeah, the guy who asked, his chances didn't change. But the other guy's chances doubled now that we know that B is going to die.
So I just wouldn't ask.
Just wouldn't ask. Yeah. It turns out you still have a 1/3 chance of dying. Just that the other guy now has 2/3 chance of dying. It's actually a very similar solution to the Monty Hall problem. It's very close. You can sort of, mathematically, it's actually exactly the same. But to get to that reasoning, you probably have to think a little bit deeper. But yeah, this will actually be this situation, right? So probability can be a little counterintuitive, but that's what makes it fun. So just be careful. You might be tempted to guess the answer for a lot of these problems, but you'll likely end up in trouble. The probability of you ending up in trouble by guessing is actually higher than you would think for other areas of math. Things can be very counterintuitive here. So it's very important that you pay attention to all the rules and sort of reason through things. A lot of times breaking things down in cases helps, just like how I did with the Monty Hall problem here. You just write out all the possibilities and see, okay, what's going on with this. But there are other methods that we can use to actually figure out the chances of something happening versus not happening. And so the rest of this chapter is going to just introduce you to some of the ideas we can use in order to get to the right answer when we want to figure out the chances of something. There's the first rule called the equal likelihood method. And this is sort of this is sort of like what it's very closely related to the original definition I gave you. There are n distinct elementary outcomes just means one particular situation that's possible of happening. And all outcomes are equally likely. Then the probability of any one outcome is 1/n. Right? So this is a rule. So for example, you roll a fair die. Right? A fair die is one that's balanced, right? So you roll it, you have an equal chance of getting any of the numbers on that die. It's not weighted or anything, everything is really fair. Let A be the probability upward face is a 3, then the probability of A would be what? 1 out of 6. Right? The chances of getting a 3 when I roll a dice is 1/6. Why? Because there's one way to get a 3. Right? There's only one face of all the 6 faces that gives you 3, but there are 6 total possibilities. Right? In fact, for any number, 1/6 would be the chances of getting that. So that's an idea of the equal likelihood method. Right? You figure out something is the same chances of everything happening, then to figure out if any one thing to happen, it's just 1 over the total. Right? So you don't have to think, what if you throw the die and spin it like that? Or what if you throws it across the room? None of that matters. There's an equal chance of this happening. There's only one way to get a 3. That's the probability. Right? No matter what happens, right? Don't try to use your intuition. Well, what if, this famous gambler threw it? What if I had this girl blow on the dice? Does that make a difference? It doesn't make a difference. 1/6 is the chances of you getting that number, right? Do not go by your intuition. It will lead you astray, okay? The K of these outcomes. Then probability of A is equal to K over N. There's another example I have in mind, but I think I actually went through that example at a later point. Should I tell you about that one?
Sure.
I can tell you. We'll finish with a couple examples then. Let's go back to one of the examples I introduced here, right, where you'll see how it works. Right, rolling a 7. What's the probability of getting a 7 when you roll 2 dice?
You can get a 1 and a 6, a 3 and a 4, 5 and a 2.
And vice versa, right?
Yeah.
So
But do you
now,
do this?
there's a systematic way to sort of do something like
By
this.
one, it's its own chance or not, too.
Okay, so the idea is here, you'd actually, one of the nicer ways to think about this is to just do a table. Let's look at the sum of the dice in a table, right? So let's say, here's the possibilities for die 1. I can get a 1, a 2, a 3, a 4, a 5, or a 6, right? And for die 2, I can get a 1, a 2, a 3, 4, 5, or a 6, right? Another thing probably will help you out with is genetics. When you guys take genetics, you're gonna probably of having a boy or a girl or things like that. Probably of getting blue eyes versus brown eyes and sort of things. This is sort of the game you play to figure things like that out. Right, so let's in each cell I put the sum of the dice, right? So let's say I have the situation where I roll a 1 on one die and a 1 on the other die. What's the sum? Well, it's 2, right? Here it would be 3, here it would be 4, 5, 6, 7, right? Some of these would be 3, 4, 5, 6, 7, 8. Some of these would be 4, 5, 6, 7, 8, 9. Some of these will be 5, 6, 7, 8, 9, 10. Some of these will be 6, 7, 8, 9, 10, 11. Some of these will be 7, 8, 9, 10, 11, 12. So I can have a sum from anywhere from 2 all the way up to 12 is the maximum sum I can get, right? The minimum is if I roll 2 1s, I get a 2. The maximum is if I roll 2 6s, I get a 12. Now I want to figure out, if I roll this die, how likely am I to get a 7? Well, number of ways to get a 7 is how many?
6.
Right? Well, you sort of count them off. There is 1, 2, 3, 4, 5, 6. There are 6 ways I can get a 7. And what are the total number of possibilities? And of course, we're assuming they're equally likely, right? Like, the person I'm playing with is not trying to scam me by giving me loaded dice, right? I'm going to think they're on the up and up. Right? Well, there are 36 total possibilities, right? This is just all the numbers in this table. 6 times 6 gives me 36 total possibilities. This means the probability of A, where A I'm taking the event the sum is a 7, is just going to be 6 out of 36, right? This is like the K, the number of ways the thing you want can happen. So it's actually 1 out of 6. It turns out getting a 7 is the most likely outcome, right? Getting any other number, it will actually be less than 1/6. Of course, the question is, oh, it's likely, so I should play the game, right? So the idea is we're going to talk about that later. It's called expectation. What return do you expect? I don't want to jump. I'm getting too excited. I'm getting ahead of myself. So the idea is if you get a 7, you get $2. If you get something else, you lose $1. Should you play the game? And we go, well, I'm more likely to get a 7 than anything else. Maybe I should play the game. Turns out. The idea behind expectation is your gain you put as a positive number times the probability, and your loss you put as a negative number. So what you would expect, I'm jumping the gun here, we'll actually come back to this. What you'd expect if you get $2 for rolling a 7 is just 2 times 1 over 6. And if you lose $1 for rolling anything else, right?
1 times 7.
1 times what? 5 over 6 is the chance of rolling anything else. Right? You can actually do that. So this would be 2 out of 6 minus 5 over 6, right? So what is that?
Negative 3. Oh.
Minus a half. So what does that tell you? You're more likely to lose. If you play this game in the long run, you'll end up 50 cents poorer than you started with. Right? So yeah, oh yeah, man, come on, man, you're likely to get a 7. I'll give you $2 if you roll a 7, $2. You only give me $1 if you roll anything else. Come on, man, look at that. There's 7 is more likely. Turns out, do not take the bait. You will lose, right? If you play long enough, you might win the first 1 or 2 times, but if you play long enough, you'll end up losing, right? So, but we'll talk about this later. I'm really jumping the gun here. We're getting too advanced now. Maybe I can finish this last example. So many examples. Okay, example. Suppose a couple
has 2 children. A. What is the probability both are girls? B.
If you look at the likelihood, it's a lot smaller.
That's true.
If you know, we're assuming boy and girl is equally likely.
Okay.
Probably of a boy is 1/2, probably of a girl is 1/2, right? Just to simplify things. I mean, if you want to get technical, then you look up the statistics and you put whatever fraction you have here. Girls are actually more likely, I think. At least they're more likely to live.
Yeah,
Yeah,
more
so
likely to
that-
survive.
Not some people.
Right, so,
Guys
Boys are more likely to
die.
be like
Yeah.
conceived, but girls are more likely to be born.
yeah.
So some reason.
But for simplicity, let's assume these numbers. If you know one child is a girl,
Human trafficking.
how do you know? Talk about this to human trafficking. Talk about for keeping things innocent. What is the probability
What's the probability that we
the other is a girl? And it seems like it'll be the same, but it's actually quite different. Right? Yeah. Knowing that, pretending that 2 are girls is completely different if you know that 1 is a girl and you want to know the chance of the other being a girl. It's like a completely different question, even though you might think these are the same, but they're actually very different questions with different answers. Just to hit it home that don't follow your intuition too much. What if you know the older child is a girl, in fact, you know her name, named Freuda. What is the probability
She's gonna get laughed at.
all 3 questions have different answers, and you think that they don't, because you're like, in all the cases, there are 2 girls, right? So why should it be different? It's actually pretty different. But time is up. Okay, I'll let you guys think about that for next time. I'll answer that next time. I want to give back the test now.